So apparently I didn't discuss this. I looked up my YouTube archives and all the videos I didn't discuss this yet, and I'm surprised. I guess I just didn't feel as if it was important enough, but it definitely is very important. The Stellar Disintegration Zone, or SDZ. I'll read the abstract out to you guys. The stellar disintegration zone is the area that separates hot Jupiters from their more evolved and evolving counterparts. Now remember, a hot Jupiter, according to the dogma, is just a Jupiter-sized object that's orbiting close in to another much hotter, much younger star. That's all it is. They say it's hot because it's close. That's their that's the way they look at things. If it's a cold Jupiter, to them it's far away. But it's not an actual, it's not a meaningful term, because it's actually, they should be saying a close-in Jupiter versus hot Jupiter, or a far-away Jupiter versus a cold Jupiter. It's the same problem they have with the ice giants. The Neptune and Uranus are ice giants. No, they're over 6,000 degrees in their interior. They're hellish in their interiors. They're not ice. There's no ice giants. That's a term that came around in the 1960s and 70s, and they stuck with it. Like, we need to get rid of that crap. They're 1.1 and 1.2 billion year old highly evolved stars. Anyways, it shows that hot Jupiters lose their thick helium and hydrogen atmospheres faster if they orbit close to a much hotter host star, which is predicted by the general theory. The SDZ on this graph is between 5 to 9 Earth radii, with a period shorter than 10 days. Now, a period is a whole year, so it takes one revolution around the host is 10 days. It's a whole year. It's shorter than that. As well, the SDZs can be different for different stars. This graph is only a generalization. So this graph only goes over a generalization of all the stars. So an SDZ could be closer in for a much more evolved star where its radiation is a lot weaker, and it could be really far away for like a blue giant where the radiation is really strong and can just destroy everything. Data is taken from various telescopes, including the Kepler, and 2,504 evolving dead stars are on the graph. The periods of the dead evolving stars on the graph do not include the ones beyond 50 days, so I cut it off at 50 days for a whole year, and objects beyond a radius of 23 Earths, so I don't include objects that have radiuses larger than 23 Earths. Data for the points on the graph is included, as well as the objects' names. This is a 52-page paper. Most of it is just the data on the stars. So all of the gaslighting that a lot of the narcissistic astronomers and critics do, say you don't have any data. Dude, it's easy to see this. Look, this area right here is the disintegration zone. Now, this is subject to change, but the reason why I have this is because when you have what I would call close-in Jupiters, according to the dogma, it's hot Jupiters. When you have these objects up here, they're orbiting so close. Now imagine the stars right here. This is how far away the companion is to the host. So this is in periods. This is actually far. This is an actual distance. This is just the period. So very close in, you have 2, 4, 6, 8. You'll see this if you pull up the paper. And this is how fast this is how many objects are orbiting that close in. But the disintegration zone right here basically means that when you have a close-in Jupiter, there reaches a point to where it's just orbiting so close in to the host that it reaches a threshold to where the gravitation on the object is not strong enough to hold on to its atmosphere. So it disintegrates a lot quicker. This is why it would just move past this little threshold really quickly and then settle in to become, to leave the rocky remains left over after the very thick atmosphere has been ripped away. And basically that's the essence of this disintegration zone. As well, to form really small objects, to form really small moons, the nebula hypothesis just completely it doesn't even explain anything really if you think about it. How to make really small moons? I'll tell you how. You have a Jupiter-sized object orbiting really close in to a much hotter star, and as the Jupiter-sized object is forming the little core in the center, the new planet, its outer atmosphere and all the material that can be used to form that planet is ripped away really, really, really quickly. So what this means is that if a Jupiter gets captured by a hotter star and orbits really close, it can't form an object that large. The object it can form is just going to be really, really, really small because it didn't have enough time to deposit the material in the center of the object to accrete the so-called planet in its interior. This is why you have really small moons. For instance, around Jupiter. When Jupiter was a hot young star, like the size of the sun, look at its moons. I mean, sure, they were probably passed from different stars in the past, but just look at the moons. Io, I think, is the one that was the gas giant when Jupiter was a large sun-like star. I think Io was the unfortunate soul that got captured by Jupiter when Jupiter was very sun-like, and Io had a very, very thick atmosphere, just like Jupiter does currently, but it was just so close in and being flung around so fast and being ripped apart that it just annihilated it, and Io really couldn't form much of an object. And Callisto and Ganymede and what's the other one? I forget the other one. But all those will probably pass from star system to star system, so they're unique. They have their own unique history, so to speak. And of course, I have all this written down here in different wording. But basically, the trick to understanding this is to understand that, of course, we have evidence of gas giants losing their atmospheres. This is direct evidence for it happening. That's why these objects right here are being ripped apart. If you look at these objects on the graph, they're probably going to be puffed out Neptunes or similar to Neptunes, and then they're going to be losing their atmosphere really quickly, and then they'll settle in to where a very thin atmosphere is left over, or if an atmosphere at all is left over. I'm not too sure if a lot of these objects down here even have the features like Earth does with the oceans and the atmosphere. A lot of them that orbit and close into their host have probably completely disintegrated. But that's just to show you how complex this is. It gets pretty crazy. And this paper was written September 29th, 2018, so it's already been a year, and I forgot to discuss this. I guess that's it, you guys. I'll go ahead and link this to the bottom of the video here, and make of it what you will.